Welcome to lesson 21, circular motion. Here's the plan for today. Let's start with the basics. In one full revolution, the object travels one circumference, 2 pi r, in a time equal to the period big T, so the speed is 2 pi r over big T. But for circular motion there's a more natural quantity, angular speed, given by omega. That's how fast you sweep out a certain angle, 2 pi radians per second, or just theta over little t. That's how the two connect very neatly. V equals omega r. Linear speed is angular speed times the radius, which is why the outside of a roundabout moves faster than the middle, even though it takes the same time to go round. And one warning that will save you: work in radians, not degrees. Radians are much more natural. Just make sure that your calculator is in the right mode. So how big is the acceleration of a mass when moving in circular motion? It's given by v squared over r, or equivalently, omega squared r. And by Newton's second law, the force needed is mv squared over r, or m omega squared r. And here's the crucial thing: that acceleration and that force point towards the centre of the circle, always inwards. The word centripetal literally means centre-seeking. When you whirl a ball on a string, the string pulls it inwards. It keeps it in circular motion. Let go and there's no more inward force, so it flies off in a straight line, exactly as Newton's first law needs it to be. Which brings us to the single biggest misconception in physics: centrifugal force. When you're going in a car round a bend and you feel flung outwards against that door, there is no outwards force. What is happening is that your body wants to carry on in a straight line, by inertia, but the door is pushing you inwards to make you turn. The sensation of being thrown outwards is just your own inertia. Never ever write centrifugal force in an exam. There are two standard cases for circular motion: horizontal circles and vertical circles, but we treat them separately because at 90 degrees sometimes the weight can affect the motion, sometimes it doesn't. Let's handle them one at a time. First, the horizontal circle, something sitting on a roundabout, viewed from above. What provides the inward force here? Friction. The friction between the object and the surface. In this case, the tyres and the road. The friction force is equal to mu times mg, the only thing pulling it towards the centre. So set friction equal to the centripetal force. Mu mg equals mv squared over r. Spin it too fast, and the friction can no longer supply enough force, and the object comes out of circular motion. That's why you slow down going around a roundabout. Now, the vertical circle, like the loop-the-loop or a fairground ride. Here mg, gravity, is in play, and it matters where you are in the loop. At the top, the centre of the circle is below you, so the net force must point downwards. Both the support force, the force that you feel against the roller coaster, added with mg equals mv squared over r. So the support force equals the centripetal force minus your weight. It's smaller and you feel light. And if you go slowly enough, that gravity alone provides all the centripetal force. The support force drops to zero and you're momentarily weightless. That's the stomach lurch at the top. At the bottom, the support force pushes up and gravity pulls down, but the net force must point towards the centre, which is upwards. So S minus mg equals mv squared over r. Rearrange, the support force equals the centripetal force plus your weight. It's larger than normal, and that's why you feel heavy, pressed into your seat at the bottom of a roller coaster. I often get confused with which equation matches with which part of the circular motion, but if you think about it conceptually, it makes a lot more sense. That's the end of the video. Thanks for watching and check out my tutoring page below.